There we go. Figure it out. We're gonna get this Edward Hugh, H-U, right? Edward. Look for Edward Hughes.
Okay. Yeah. Wait.
Zero.
No, Genesis 85.
Alright, everyone, let's calm down. We're already a little bit late.
I'm not going to start laughing.
I know it's Low Show Friday, so actually it looks like enough people wandered in. There's your test average, 85. Real quick, we get the doors. Last semester, when I taught Maine with the same course, did you guess what the average was? 71. 71 last semester, same class, same material. Woo! 85. I would like to thank myself. And honestly, I didn't feel like that test was any harder. It did cover different material, so there may be a little bit of something with that. And come on, folks, we're already a little bit late. Now, there was different material, because remember, you've only taken this class, but there was a part that I told you that I had to cut out from this section, which is about velocity of gases, which was kind of hard. So because of that, the tests were not identical. I think they were identical in hardness, and usually this number is quite equal. But don't get slack on this, because last semester they may have scored 71, but then they got a lot better, which is generally true. And then I told them, I was like, hey guys, it looks like you have a kind of a mid-B average, which is really high. And that's your average. They had that by the end of the semester. And I was just trying to make them not nervous for the final. They ended up slacking off. I think I oversold it. And they ended up slacking off, and then their final, they bombed the final. And they ended up being one of the lowest scoring classes I had, because they completely wiped out on the final. Because I think they didn't prepare for it, because I kind of stroked their ego. I think too much. I don't know if it was really me or not. I don't know. But that's what happened. So don't get complacent. Number two, the second test will be harder. Because we're doing more and more advanced stuff. It's inevitable, right? We started out with high school P equals NRT. We're starting the second test not at that level. It will correspondingly be harder. So don't slack off. Second test is going to be naturally harder, because we're going to have gas expands and gas contracts, which is going to be on the next homework. And you're going to have to deck out all 12 variables. And remember, 4 conditions giving 48 different things you can calculate. That's the second test. It's a bit harder than what you had. You had to give me like 5 or 6. Now you got 12 for a gas expands and gas contract. We're also going to get to reactive delta Gs, right? Because we're going to cover delta G today. And then we're going to finish up largely by the end of the week, into next week. We're going to finish up this whole gas expands and gas contracts, and then we're going to get to actual chemical reactions. So the thermochemistry chemical reactions. And a lot of what you did in freshman was wrong, by the way. Simplifications to the point where the material was actually incorrect. The real way to calculate this stuff is unfortunately much harder. And that will be on the second test. So don't take me. I'm returning the test after the second hour. Sorry, you people will go monkey show. Go monkey on me if I put them out right now, or even in between classes. Into the next class, all right? But you're going to be pretty pleasantly surprised. And if you didn't do well, you already heard it from me. So anyway, so the next hour, actually, I have those. What happened? Okay. The next hour, what I have is we're going to start doing a lot of derivations And so we're going to start practicing that. It's going to be kind of like a second lecture because we're kind of a little bit behind on the calendar, like 2 days behind last time I checked. So the next hour I'm going to use as sort of a second lecture, but I've got only 2.5 pages of notes, which is only half the class. I also brought the test with me. I can go over test questions, point out where did I hide answers to questions and other questions so you can spot them easier next time. Point them all out so that way next time, like I say, you'll find them easier. And that's fine. That's smart. And I want you all to be smart. I don't care how you're smart. It doesn't matter as long as you're smart. And also, it'll help you get inside of my mind. It'll help you answer test questions. I've got candy in the fridge. I also entertain questions. I know you folks have been very good about asking me questions, which I appreciate. So again, the next lecture, practice for the next problem set. This problem set I gave you, it's kind of easy. I went easy on you this time. It's not bad, because I just felt like giving you a break. And anyway, so you saw you had to, I hope you like the first 3 questions. It's like permutations and calculating entropies of a knight on the chessboard, like we did with the X and 3 circles, except we got knights on the chessboard now. So I hope it's kind of fun. And then the next problem set will be kind of significantly harder. We're going to start doing more thermoderivations. Like the last question on the test, prove to me that dHdP at constant t was 0. It's like that, but they're kind of harder. But what we do is we work them over and over and over again until they become second nature, and then it's just not a problem. I forgot to write my mouth. Any questions? We're okay? Right, I know, we just started. Question?
Yeah. You have a formula for delta S. And I looked at it, I said, I could write that same formula for delta U. Where's the mistake in my thinking?
So yeah, as always, I always review what we talked about last time, so I was going to bring this up anyway. CV per mole. Now I'm writing this way. It's really CV ln TF over TI, but remember I'm giving you the molar heat capacity. Just remember that these two are the actual heat capacity per mole. Let's see, plus NR. See, I have done this too many times, obviously, I just memorized. And you don't have to, it's on your cheat sheet. Now, let's see here. Now, this is almost the change in U, except that's a natural log. U is CV delta T. Natural log of almost delta T. Well, sorry, you know, we can write it down like this, right? MCV ln T minus ln TI. Okay, it's not TF minus TI, it's natural log of TF minus TI. And that's the difference. Okay, yeah, I see that's a little different. Notice that I also killed off the units. So that the units are not the same. So this is clearly not U. This is joules per K, not joules. And that's because when I took the natural log of T, I killed off its units, because natural logs can't have units. And then the same true over here. What I would normally have is, this would be work. If this was change in U, this would be the work term, this would be the heat term, and the work term would be PdV. And again, I don't have dV, I have the change in the natural logs, not the change in. So that's the difference. So we're okay? And remember, and I'm going to rederive this a couple of different ways. There's so many ways to rederive this. And in the second hour, I'm also going to show you alternative ways to answer some of the questions that you came up with that I didn't know about. It's kind of cool when you do that. So anyway, okay, so there's our formula for entropy, changes in entropy of the system. And remember, we talked at length about the surroundings and the total, and that's where it gets to be a bit of a biz knocker. Again, real quick, now we also talked about KBLN, number of microstates. You have examples on your homework. It won't get harder. I'm going to have that on the test. It won't get harder than that. So you have some idea what, not the change of S is, but what S is. They're not the same. And if you're more interested, you go to grad school and take an entire semester, and then you can work those problems as easily as I did, because again, I can't get across how to do that unless we spend all semester on it. Let's see, what else did we do? We did the cloudiness inequality, change in S, minus the change in heat over temperature, greater than or equal to 0. Equal to is when the process is reversible, in which case this is entropy minus system entropy minus system entropy, in which case it is 0. If this is not reversible, then this is irreversible, adiabatic, or isothermal, in which case the cloudiness inequality applies. And remember, that comes from understanding reversible work, kind of a roundabout thing. Then I said a constant constant volume, I inserted the change in U, just for the hell of it. And now I'm gonna do this more explicitly. Now remember that this is the total entropy. This says that the total entropy increases, and I did that last time, I don't want to repeat myself. And so then I have the change in U minus TDS is less than or equal to 0, and then that means that constant S, the change in U, must be less than or equal to 0 for total entropy to increase, making the process spontaneous. But this this reaction must occur in a closed vessel, which is dangerous, and somehow I have to keep entropy constant. Now you could do that. I know I was joking around last time, right before the end of class, about how do you keep entropy constant. I said the entropy fish does it. There's no entropy fish. You could do things adiabatically and reversibly. Invent an adiabatic reversible machine. Not that you can get close. People are clever. There are machines that are kind of close to adiabatic reversible. And then you actually can do things at constant volume and constant entropy. And whatever's going on inside that adiabatic reversible machine, if it's spontaneous, throw out delta G. Delta G doesn't tell you anything. A, H, or anything. It's change in U. That decides spontaneous. Remember, I reversed your notion of what is spontaneous. Oh, in high school, calculate the G's of the products minus the G's of the reactants, and hey, it's spontaneous. And I remember looking at that and saying, why? But why does H minus TS, why is that so special and it decides everything? I never understood it until I took this class. So, okay, and then I also pointed out if S and P were constant, then change in H being less than 0 equals spontaneous. And I'm not going to prove that. It's just you just change H instead of Q. It's really a 5-year-old can do that. I'm pretty sure. I'm sure they wouldn't understand it, but I bet they could do it. So, all right, new stuff. Wow, I blew 1/3 of the class when I was talking about new stuff. I wonder where this snail's pace. Now we're going to get into the new energy functions. And so what I want to do is remind you of Legendre transforms, because now we've got Legendre transforms coming up the wazoo. And that is the change of a function, and I'll keep it of a single variable. I have to do this. I have to change the next, so I'm going to keep it a single variable. Let's make f u, and x will be v then. And then I have the change in u is the change in u per volume, in terms of change in volume. And I note that this is minus p. Remember exterior. Often I'll make it interior because the change in u is exact. And so here I'll just say it's just the same. Remember, no subscript. That's the system. I can just say that because u again is exact. And the point is, it actually makes things easier. Don't think of this as like, oh, yeah, now I got to remember that. No, you don't. Just stick with this. It makes it easier. That's easy to remember. Okay, and so remember that the Legendre transform gives me a new function, which is of a new variable. And I hope that question on the test was rather easy because it was just absolutely silly. Take the function and subtract the variable you want to remove the dependence on times its conjugate. The conjugate being defined as this. And there you go. And therefore, that's why H is equal to U minus V times minus P, which is the conjugate. That looks awful. It's U plus PP. It's still energy, it just has a natural function of pressure, not volume. I've done this a million times, I don't even know what I'm talking about. Okay, so reminder stuff. God, I still haven't gone over anything new. Let's start going over new stuff. Change in U is the change in heat. What's the change in work? Again, that's one of those things that got a star by it. And I know that change in work. I should have done this differently. Sorry, I'm going to kind of screw this up. A little bit of an aside. Change in entropy is the change in heat over temperature. Therefore, the change in heat is TDS. And because I know this is reversible heat, but again, it doesn't matter because U again is exact. TDS. Okay, now folks, This guy, for the next 2 weeks, you're going to see this over and over again. This is where, as I mentioned to you, we're going to start doing a lot of derivations. The HDP at constant T, your last question on the last test is 0. We're going to do that. I mean, how many letters have I got to work with? D blah, constant blah is what? Is it 0? Is it positive? Is it negative? I've got so many letters to choose from that I have an infinite number of questions to ask. And I'll try to make them meaningful, not just to play musical chair with the alphabet, but it all starts here. And so you don't have to memorize that. Okay, this gets a star. This already got a star, that got a star, so you don't have to memorize this. You already know what work is. God knows that's been hammered into you. I'm not even going to write it down. God knows we've done that a zillion times. Okay, so now I want to point out that this is the change in U with respect to V at constant. Take a guess, constant what? All right, remember this will be on the cheat sheet. Okay, so again, look at that and tell me what's constant. Louder.
Us.
Entropy, right? But look, if you really are having a hard time with this, I swear to God, just do this. There. There. It really can be that easy. Okay, and then this is the U, the S. Constant what? Constant what? Volume, right. Oh, sorry, that looks awful. OCD. Okay. So you can see that this is minus P, and that this is temperature, plus temperature. I'll put a plus there to remind you. Now remember that because IUPAC decided that work had to be minus pressure times change in volume, when we do these manipulations, remember that temperature and entropy are going to go in a positive direction, and pressure and volume will always go in the negative direction in terms of sign. And it's just because of that. If IUPAC had just chosen not to do that like the engineers do, then these would be much more similar. You'll see what I mean here in a minute. But now, okay guys, I can't emphasize enough. Put a square, not a star. You don't have to memorize that, but put a square by that because you're going to need to know that. Okay. All right, again, this has really been a bunch of review. I haven't expressed the change in U that way before, but I hopefully I haven't blown your head off. Now, let's start doing more Fourier transforms, Legendre transforms. Okay, now I Legendre transformed use dependence on V with H. Now, what I want to do is I want to Legendre transform use dependence on what? It's dependent on V and what? S, right. U is a function of V and S. I Legendre transformed the V dependence, give me H. And H was kind of useful. If pressure is constant, it becomes heat. H has its role. That was nice. Now I want to get rid of the entropy dependence because entropy, I have temperature regulators, but I don't have entropy regulators. So I would like to get rid of the entropy dependence and put it on something else. So I'm going to subtract what? I want to get rid of what again? I have to multiply by its conjugate, which is? I've lost it. What? Come on. D, right, see? Change in S times T, right? So the conjugates are multiplied by each other. That's what's special about conjugates. Now, since this is a class about energy, the thing times its conjugate will equal energy. Now, I guess there's other things I could come up with, but that's not true. But I'm only doing calculations on energy. And always, because I'm always working with energy functions, because that's what the only thing I ever care about, conjugates times their variable will always be energy. And again, I guess there's other ways to do that, but whatever. Okay, this is a new function. It's a function of T and what? The pressure? What? What's it a function of? Volume, right. I didn't get rid of the volume. And this is Helmholtz. Helmholtz energy. Okay, I won't spell energy. So anyway, all right, it's a new character, it's a new thing you have to calculate when a gas expands and gas contracts. Guess what I got looking for? I got delta G. But let's work with this guy. This guy's kind of easy. And this guy is going to be our friend when volume is constant and temperature is constant, which is something I can do quite easily. Now, okay, tell me this. Okay, so A has lots of properties. We're going to go through every one of them. That'll be most of the lecture. If the change in A is to be negative, is to represent a total change of entropy, which is positive, good, we'll call that good, what variables must be constant? Come on, it's right in front of you. E? No, V. V and T. V and T. Right, so I'm pretty sure if I hold V and T constant, that I will find the total entropy change via the Clausius inequality. Well, the decrease in energy will be a positive increase in total entropy. And that, by the way, comes from, you see why we always think, okay, increase is good, more food, and we always think that is good. But when it comes to this representation of total entropy, it didn't have to be negative because of this minus t. That minus sign is doing it. So remember, increases in stuff are generally good, but not energy. Decreases in energy, let's call that good, that's spontaneous, and it all comes down to that minus t right there. That's the origin of why changes in energy go downhill, minus right there. That's what did it the whole time. Okay, this is going to help you on your homework, so come on guys, we're a little out today, all right? So let me do it. I'm going to have to start the derivation, and then I'm going to have to, sorry, what am I doing? I'm going to start the derivation, then I have to do another side derivation. And then I add the two together, which is annoying, but, okay, what should I hold constant? Give me the first thing to hold constant.
G.
V, yes, V, right. I don't want to hold constant first, that doesn't help right now. Constant V. Okay, times minus t. And now I've got the change in u, minus s, TdS, and equal to 0. Okay. Now I'm going to insert the above for the change in u. And so the homework question is you're going to do the same thing for the change in g. It's a little bit harder. And I'm going to point out where I'm going to do something that you will repeat to a different level on the homework, so you can do that. Okay, so now the change, what I'm doing is inserting for the change in u. Write that in your notes. I'm not going to write it down here. I'm going to insert that for this. So write that down in your notes in case you get confused. PdV plus TdS minus TdS is greater than or equal to 0. Okay. Now this is where I have to do a side derivation, and that is on A. I'm doing this right. Okay. So what I have to do is, if A is U minus TS, then the change in A is the change in U. I'm going to go ahead and just do this next step just automatically because you need to be at this level at this point. TdS plus SPT. Right? So again, question?
Is the sign over there, du minus dvc, is the sign distinctly correct?
Yeah, it should flip.
Oh, I should have flipped. You're right. Oh, thank you. Oh, dear God. Yeah, I wasn't paying attention. Yeah, greater than and less than signs are actually relatively easy, but that's just one of the things that they're a little bit tricky with. Okay, let me insert the change in A is now
SDT TDS. You wrote the same thing
yeah,
twice.
Sorry. You see, I'm not looking at my notes here. I screw up a lot. Thank you. TDS. Sorry. Split that up. Okay, I think I have a hang up on this. Okay, so I've got minus PDD plus TDS. No, minus, Jesus. Good God, folks. Sorry, come on, all right? A little all over the place right now. Sorry about that. Minus SDT, minus TDS. Okay, those cancel. Minus PDT. Minus SPT. Okay. Again, this is changing it. Now what I'm going to do is, you know, I shouldn't have done this, should not have. I think I made a mistake somewhere. Minus CDS. What have I done? I think I've made, hold on folks, let me back up a bit. I think I've made some kind of stupid mistake somewhere. Yeah, why am I doing that? Yeah, that doesn't add up. I don't know what I've done wrong. Sorry about that. Let me just go back to this statement, so just cross it out. Sorry about that. Yeah, I know. Okay, let me go back here. Sorry, I'm a little cross-eyed with what I meant to do. Okay, here's the clever trick. Keep this. Okay, so this is on your homework. All right, this is the step that's on your homework. Except it's a little different because you go for delta G. Okay, now I've retained this. Nothing has changed. And then my cleverness is to add 0. And that is I'm going to subtract. Just so you don't get lost on your notes, write that down. Notice that I just simply added 0. And from this part, look at that. And you see that? And so it's a little, this is give me a little cross-eyed, but just notice I've taken something that we've done a couple of times now that's not hard, and I simply added 0 to it. Now, if I bracket things the right way, and I look at my derivation of A, then I see that I've got the change in A plus the leftover term. There we go. All right, I never quite put it this way before. I hope this is a bit easier. I thought this might be a little bit easier when I was looking at my notes to show it this way. And if not, that's why we have office hours. If not, watch the video again. Hopefully it'll be clear. Okay, now I've kept, again, I had this expression for total entropy. I multiplied by minus T, which kind of threw a little bit of a monkey wrench. It's not units of entropy anymore, but it's still, it's total entropy times minus temperature. So now it's in units of joules, and it won't increase, it has to decrease to be spontaneous, again because of the minus sign. Now I'd like to convert this into a form of energy, but now I'm stuck. I don't have just A. Someone unstick me. What do? Now remember before I had U is less than 0, I had H is less than 0. I want to have A is less than 0, but I don't. So what do? What was it?
Constant T.
Yeah, constant T, right. Stipulations. And constant temperature. Now the change in A must be less than equal to 0, and that is spontaneous. But it does require a constant B and T. Now here's the dangerous thing, that's realistic. Now I can build an enclosed engine that's reversible and adiabatic, which means that the change in U matters in terms of spontaneity, in terms of what happens inside the engine, what drives the engine. I don't really have many reversible adiabatic engines, so I don't really care about changing U too much. I do have closed vessels. Again, I always emphasize that's not something we normally do. I do have closed vessels. I do chemical reactions in closed vessels, and I almost always keep temperature constant in anything, any process I do. And even when I'm changing temperature, Just a funny thing for you, any of you in organic chemists, organic groups, a couple, if any of you end up in, so, hopefully you'll go get a PhD. And you'll do 20-step syntheses of natural products. It sounds kind of painful, but that saves you from cancer. So a friend of mine did that. He did 20 steps to make a natural product. He got a PhD. Then he goes to Merck, and they said to him, like, well, we appreciate your skill and knowledge, but reality is when we make a drug, we just throw all the ingredients into an autoclave and bake the hell out of it. And we make 50 things at once, but one of them's our drug. And so we turned your 50 steps into one step in a very hard separation. And so they actually prefer to do things that way. Also, power plants. Power plants work on A. They don't work on G. Because the turbines are enclosed vessels. Not perfectly, but that's a better representation of a power plant. They don't care about G, they care about A. Also, where does A come from? When it's Helmholtz, why isn't it H? Well, H was taken. Anyone know, what's the German word for work?
Arbeit.
Arbeit.
Yeah.
That's sort of Scottish, isn't it? Yeah, Arbeit. So that's where German for work. Let me explain why. Why is it German for work? Let me give that to you here. We're going to work with A a bit, and then we'll get to G. And that will be about 1/3 of your homework questions. Oh, by the way, so I'm going to give you your homeworks back at the end of the next hour. If you find yourself stressed, I know this sounds stupid, I'm getting old, I know, but I do find if you close your eyes and just, close your eyes and count to 10, screaming in German is a real relaxer, that'll totally take your stress and put it somewhere else. Okay, so other properties of A. Now remember, all right, so when I had volume constants and that was it, U became heat. When I had pressure constant, which is more useful, H became heat. Heat's important because the lights are on because somewhere a coal is being burnt, right? Or nuclear fuel is being burnt. And so heat's important. Now let's see what A will do. Now I've already done its natural variables. It's total entropy, it's minus temperature times total entropy. So I want that to be negative, so total entropy increases, temperature is always positive. Anyway, so let's look at other things. I'll just write this down. I'll just write it down again. And I'll get it right this time, which is a little bit more useful. And then that's PDB. So you're going to do, and I'm going to ask you to do this on the test. TDS, SPT. Definitely expect something like this on the test. Because this is how you transform, this is how you do all these derivations I'm going to be asking you to do. Okay, so at constant temperature, this is minus PdV. And what would this be? What's minus PdV? What is it? Work. What kind of work? Reversible, right? Because that's interior pressure. Okay, so A is important because when you hold one of its natural variables constant, it becomes the maximum work the machine can do. So again, before with H and U, I could get the heat of the thing, and now I can get the work of the thing. I just have to switch to a different thing. Yeah, so that's actually where it got its name, Arbeit, from the fact that it actually represents the maximum work a machine can do. Again, we draw special things out of these energy functions when we hold one or both of their natural variables constant. You're going to see that over and over and over again. And again, these guys here, they're terribly important. It's up there. I have it for you. Where's you? Here, I'll just write down U. Okay, so again, this guy is terribly important. And of course, I'll give it to you unless I ask you to derive it. U is work plus TDS, that's heat. Let's put a square around that. Let's do H. H is U plus PV. So let's make this change in H. Okay, and then this is, got it right here, minus PdV plus TDS plus PdV plus a V, PdV. Scratch. square around that one. And again, remember, I think I started out with something like this on your homework, so you're going to see where we're going to do all these derivations starting from these guys in squares. We're going to do G next. What are H's natural variables? Okay, T and P, S and P, right. Hopefully you know the pressure because we've been doing that for a while. Okay, G. Now, when it comes to your homework, I'm going to have you do this part for G. And so you're going to basically add 0, but you're going to add another 0. I'll go ahead and tell you. Add another 0 by adding P dV plus dVp, and that gives you the answer. So, being a cheap rate, not an easy one. Well, vice versa in that case. Okay, let's do G, and I'm going to back off for G for a while. But God knows you've had Gibbs energy since high school, so you're probably wondering about it. Okay, let's take U. Now, U again is a function of S and V. Neither are useful. Don't like to do things in closed volume. I don't have an entropy regulator. I want to get rid of both. All right, how do I get rid of? Sorry if I screwed up those. Sorry about that. Use a function of V and S. How do I get rid of the volume dependence? What do I do? Oh, come on. Subtract what?
Natural variable.
Natural variable of what? The thing I want to get rid of, which is volume. Right? Get rid of the variable times its conjugate. It happens to be negative. Thank you, I. And now I want to get rid of. I want to get rid of the. I want to get rid of S now. So what do I subtract? I heard TD. That's toilet paper. TS, right. Subtract S and its conjugate, which is T. Plus PV. Okay, so you see, again, where IUPAC really kind of screwed us is that whenever you're messing with PV, you always, in TS, when you're manipulating, you always end up with the minus sign in one and not the other, or vice versa. It's the one thing that makes it just a little bit harder than that. Okay, and this, of course, is, give me a letter, G, give me a letter. G, Gibbs energy. Okay, now, this is not always useful, but this is, because it tells me the natural variables. Oh God, this is a pain in the ass. PV. Now, remember I told you a long time ago to get used to this? Now you see why? Okay, and you can see this would be a reasonable test question, right? It's a lot of stuff, but it's not bad. Now, of course, insert U. God, do I have enough room? Minus PVP plus TDS plus PV plus VDP. It's just a lot of stuff. See, this is why I like this as a test question, because it's meaningful. And yeah, it takes a bit of effort, but it's not exactly hard either. All right, those are gone. Those are gone. And that's it. PDP minus SPT. Okay, G is a natural function. What are the natural variables? Pressure and temperature, right there and right there. So again, if I can, okay, what else can I do on the next step? Throw some random thing at you and have it with squiggly lines and goats and horses and say, what are the natural variables? And then you go for that. You need to understand why. I hope that that's not true, but even if you don't understand why, that's where you'll find the answer. So, of course, I hope that's not the case, because that makes it kind of useless. Okay, so that's G. And we're going to stay off of G for a while. And on your homework, you're going to prove that you're going to start with the Clausius inequality, and you're going to start making stipulations on what's held constant. And then you're going to add a 0, minus STT plus STT plus PDV minus PDV and all that jazz. And then you're going to show me that when you hold these things constant, that the change in G, which is negative, is total entropy positive, which is spontaneous. Right? So that's on your homework. And I could come up with something like that on your test as well. Okay, just a few minutes. So folks, a little randy today, so maybe it's mating season. But let's talk a little bit about entropy. Now that I've introduced entropy into the room, I can show you some manipulations with it and show some kind of derivations that are real easy. Prove some of the derivations I did before. Okay, so let's call this properties of S. Because this next week is just going to be doing derivation after derivation. And again, I will not just make them a soup of letters. I will try to say, we're going to do this and understand how the power plant works. We're going to do this and it's going to say something about the motor in your cycle. And anyway, so let's just get into it and just practice, right? Practice is good. So I imagine I've designed a question where I start out with the change in U, and as usual, I will always, you gotta get used to this. This is second nature for me, but of course we all know I've been doing this for too long. Okay, so I give you this, and my question is, what is the change in S with temperature at constant volume? That's the question. Okay, let me write that down. So that was the question that was asked. The question is, change in S with temperature, right? Yeah, change in temperature at constant volume. What? Okay, it's a homework question, it's a test question, I don't know. And as you saw on the test, I start you out. I'm not going to leave you just hanging there trying to guess what to do. Okay, now, again, I can just do the derivation, or I can get you to think about it and then do the derivation. Okay, so this is what I'm looking for. So I need to get this guy. Now I'm giving you this. I'm going to give you this because this is the best way to start out. You can start out a couple. You can start out 4 different ways. U, H, A, or G. You can start out with U, H, A, or G. I'm telling you that all of them will work, but this is going to give you the quickest route to the answer because I've done them. All right, so I know that. Now tell me, what's my next step? I need to get this in here. How do I do it? It's real obvious.
Divide by dt.
Right, divide by dt. Right, yeah, child's play. Now I've done this, now multivariable calculus, I have to hold something constant. You can't be changing 3 things at once. You can only change, one and then the other while something's held constant. So what hold constant? Right, because that's what I'm looking for. Right. Right, so you see with the starting point, which I will give you, because otherwise you're just wasting your time. I don't believe in wasting time. This is very easy. Okay, I can eliminate a term. There you go. By the way, on the test, a lot of you ended up with PD at constant B, and you said it was 0. No, it wasn't 0. You're going to find out anyway. So that I can eliminate. And okay, this guy? CV, right. U is change in temperature. Remember, at constant volume, this is heat. The heat is equal to CV, change in temperature. And therefore, this is CV. If I divide by T, change in S, change in C. Okay. If temperature raises, does entropy raise? Yeah, of course it does. Right, because it's positive. Remember, what I'm going to do is have you derive it, or I'll give it to you and say, does it go up or down? Now, here's another thing. All right, I've asked you to derive this in question 1. Question 2, prove it's correct. And how do you know it's right? Let's do this. Sorry, let me switch them. Sorry about this. And remember, this is where, remember we can play musical chairs with partials. They're just, it's like A over B. Look familiar? All right, that's delta S. Is that correct? Yeah, of course it's correct. Remember we derived this, actually I forgot how we derived it. Anyway, well I knew we derived it before we got this, but where's my volume term? Remember I gave you that one general term, what was it?
Constant.
It's constant, right. That second term was naturally not there. It should not have shown up because I said it shouldn't show up because I derived it that way. I know it's correct. Let's do more. Let's do a couple of hundred, like on your homework. Let's do changing S with respect to volume. Am I doing enough time? Yeah, I got plenty of time. I'll just do 1 or 2 more. Let me do 1 or 2 more. Get you used to this. These are, by the way, These will not be in the next to last, these will not be in the derivation section, they won't be in the next to last section. These will be in the middle hard section. This derivation is in the middle hard section, just so you know where this stands in the pecking order of the kinds of questions I'm going to ask. I just did temperature and what am I going to do? Okay. Again, you can see the potpourri. The potpourri of letters I can ask is infinite, and that's why I still have never repeated a question yet on a test or even on a homework, because there's so many of these freaking things I can do, and you're going to see even more of that in the next hour. But yeah, so anyway, again, this is not the life in the universe and everything. This is not the derivational section. This is the section before that. So I'm telling you, this is actually going to be the easier side of the spectrum. Now, just to get your instincts up, I have volume here. Would you like to guess A, H, G, or A? Which do you think I should start with? I should have clickers, shouldn't I? Yeah. Like, no? Someone said, no, you shouldn't.
Yeah, I hope it's perfect.
You, God damn it, it's you. It's you. Go with you. Why? Why go with you? Okay, here's why not A and G. Because they don't have the change in S, they have S in them.
Oh, yeah.
Right, now you don't, right, so I have change in S, so that means that I have a good recipe for the change in S. Now, I've got, U has a change in volume in it, and that means that when I divide, obviously I'm going to ultimately divide by change in volume. That's going to make this one work a bit easier than this one. I can do U or H because they have DS in them. I can do either, but this one is faster. Right, this one's going to be faster, so let's write that down. TDS minus PDV. Obviously I divide by dV. And I'm going to keep T constant. Okay, and I have to admit I'm a bit. Oh yeah, yeah. Okay. Come on, right? Just 2 minutes. For 2 minutes. 2 things I can eliminate. Give them to me. Okay, what? 1 and 0. So some of you kind of screwed this up when you had divided things. Sometimes when you had dV, some of you had dV, you decided it was 0. It's not, it's 1. And this is the case. I'm doing perfect gases, by the way. And so I didn't say that. I should have said that. Perfect gases, remember, for perfect gases, it's definitely 0. And that means that the change in S with respect to volume and constant temperature is minus E over T. Is this right? Yeah, which is R over V. You know, remember, you don't have to simplify things. Another thing, because we'll talk about the test in the next hour, some of you simplify things. There's not many examples, but 1 or 2 of you decided to take the initiative to simplify things and you did it wrong. I can't give you full credit on that. You wrote down the wrong answer. Careful about that. Remember, I'm not a big fan of simplification. All right, real quick, we're going to take a break. In 10 seconds, is it right?
Yes.
I know. MR, V, or V. Integrate. Therefore, delta S is NRLM VF over VI, which is correct. Where's our temperature term?
Constant.
Constant T should not be there. 10 minutes break. Don't let them steal my camera. You know they'll steal my camera. I'm paranoid. All right, 10 minutes break. I'm coming back with your test, but I'm not going to distribute it until the end.